The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The key point of the previous lecture was to simplify the equations for refraction from a spherical surface such that we can write them in a simple form. And okay, what I just said was a redundancy, but we want to simplify them. I should have said we want to simplify them so that we can write them in a linearized form. And the linearized form is actually very useful because with this form, as I'm about to show, we can use a very familiar form of math, namely linear algebra, matrices, and we can ray trace through almost arbitrarily complex optical systems. Of course, there's a downside that, the way, if we ray trace this way, we do not really get very accurate results. Our results, as we discussed last time, are only accurate within the paraxial approximation. On the other hand, if we do this analysis even approximately, we can get an idea of how the optical system behaves, and then if we get this approximate design, this approximate idea, then we can plug the system into a more sophisticated numerical tool. For example, Zemax or Code5. There's a number of different optical design software suites available, and then we can actually get a more accurate analysis of how the optical system should behave. So the other reason why we write these matrices is that they give us actually quite a bit of intuition about the basic properties of optical systems. So it is really worthwhile to do this first every time we face an optics problem before we jump into the numerical analysis. And for those of you who really have sort of real-life problems to solve, and you really need to go to software, we will tell you later during the class, we will give you some information about what types of software are available and what you can do with those. But generally, this idea of using paraxial optics is very powerful in order to understand optical systems. So the summary then of what paraxial optics tells us is summarized, is shown on this slide over here. The most important is the result shown on the right that allows you to write the angle of departure of a ray to the right-hand side of a curved interface and the elevation of the ray with respect to the right-hand side interface. It allows you to write them as functions of the corresponding quantities on the left-hand side of the interface. And as you can see there, it actually looks like a 2 by 2 set of vectors which are related by a 2 by 2 matrix. And the matrix is not very interesting. As you can see, the most relevant, the most interesting element is the element on the first row, second column, which equals the index of refraction to the right of the interface minus the index of refraction to the left, divided by the radius of curvature of the spherical interface. And of course, the radius of curvature is simply the radius of the sphere, if we're talking about the sphere. And then the other result that we put here, and looks like propagation through free space, it looks kind of too much trouble really for what it's worth, but you will see in a second that this is actually a very useful tool to have in mind. Only thing that says is that the ray, as it propagates from the left over a distance d, if it propagates through free space, then what happens is the elevation of the ray changes, but the angle of propagation does not change. So this verifies what we know from Fermat's principle, that a ray propagating in uniform space, it minimizes its path. Therefore, it must propagate in a straight line, because the straight line is the minimum path between 2 points. Now, you might be wondering, we talked last time about ellipsoidal surfaces, hyperboloidal surfaces, and spherical surfaces, you might wonder why did we do this analysis in the context of a sphere? Well, the answer is it doesn't matter very much because all of these three possibilities, ellipsoids, hyperboloids, and spheres, near the axis, they actually all look kind of the same. If you compare a sphere, so I should specify now what I mean by axis. So in the case of a sphere, as Professor Shepard pointed out last time, in the case of a sphere, really any line going through the center of the sphere acts as the optical axis. But for the hyperboloid and the ellipsoid, that's not true. There's a very well-defined major axis and minor axis for the surfaces. And if you match, and it turns out you can match the curvature of these surfaces with the curvature of a sphere, so that near a common axis they all look the same, as I've done in this diagram. It's a little bit of an algebraic mess to actually work out how to do this. So I didn't do it on the slide. The idea is basically to do a Taylor series expansion on the expressions that describe all those surfaces. And then when you do that, each one of those is described by a different set of coefficients. So what you can do then is you can match the coefficients in order to match the curvatures. So I will let the graduate version of the class, those of you who are taking 2.7.10, as a homework, I will let you work out one of this, a simple case for matching, I forget, I think it is matching an ellipsoid to a sphere. So I'll let you do that. What I really want you to live with out of this lecture for now is that the paraxial analysis remains valid for all three surfaces, okay? As long as we match the curvature of the sphere, ellipse, and hyperboloid, and we constrain ourselves to the paraxial regime, then our results remain approximately correct. So this is kind of another useful property of the paraxial approximation, that it is not only valid for a sphere, but it is also valid for other surfaces of revolution, provided the curvature near the center of the surfaces matches the curvature of the corresponding sphere. Okay. Yeah, push the button, please. Yeah, so that's a good question.
Could you repeat the question? We didn't hear the question.
The angle was if there is the question was if there is an angle that we consider as a cutoff for the breakdown of the paraxial approximation. So the accurate answer is 0. Any angle other than 0 violates the paraxial approximation. In actuality, you can calculate, with the help from this Taylor series actually that I showed on the previous slide, you can calculate the accuracy of the approximation. So treat this as a first order of a Taylor series expansion, and then you can calculate what is the next order accuracy. So this is actually algebraically quite complex, and typically we resort to software to do it for us, numerical software. As a rule of thumb, anything in the range below 30 degrees, you can kind of trust the paraxial approximation, but that's a rule of thumb. In some cases not true, in some cases you need more accuracy, so the guideline is something like that. But for example, for sure, if you have a ray propagating at 80 degrees, you know for sure the approximation breaks. If it goes at 1, 2, 3 degrees, then most likely you're okay. And then there's a gray area that you have to be a little bit more careful. If you are demanded, if the accuracy demanded by the application is much higher, then you have to be more careful. There's also surfaces that are not very well described by this at all. For example, a cubic. If you make a refractive interface that looks like a cubic surface, would look kind of like this, right? And then this totally breaks down, right? So you have to be really, you have to go to non-paraxial analysis. The other thing I want to discuss is in the previous, all of the previous equations, I wrote down ray elevations and ray angles. But I was not very careful about defining the signs of these angles, namely whether they go up or down or left or right and so on. I left this a little bit vague. So this may appear, again, this may appear like too much trouble for nothing, but you will see as we go later on with the lecture today, you will see that this is very useful and very highly non-trivial aspect of geometrical optics, namely the conventions of the signs for when the quantities that we're dealing with are positive or negative. So bear with me for a second, and I will show examples of how this works later. So I will read this because I don't know of a better way to do it. I will read it, and then as I read, please look down at the slide, and you will see on the left-hand side I have examples of all these quantities being positive, and on the right-hand side I have example of all these quantities being negative. Okay, so the convention number one is that the light always travels from left to right. So you know immediately when someone draws an optical system or attempts to draw an optical system, you know immediately if this person knows their optics or not by the way they pick the light propagation. If they show light rays going from right to left, it means they don't know optics. Or if they learned optics, they learned it very deficiently. So always light goes from left to right in these diagrams. There's one exception, of course. Can anybody guess one exception that I'm not dealing with here? Mirror. Push the button.
Mirror.
Mirrors. Yeah. So in this diagram over here, I do not consider mirrors yet. We will deal with mirrors later in about a week, and then we'll see a revised set of sign conventions. But as long as there's no mirrors in your optical system, if you have what is called a purely dioptric optical system, then the light is always going from left to right. Taking this as a given, then we define the positive and negative radii of curvature as shown over here. So if the surface is convex towards the left, then we'll call it positive. Okay? Then this sounds a little bit weird. It says that longitudinal distances are positive if pointing to the right. I'll show you an example a little bit later where a distance can become negative by pointing to the left. But for now, take this definition for granted. The same is for lateral distances, that is measured perpendicular to the optical axis. If they point up, then they're called positive. If they point down, they're called negative. And finally, angles are positive if they are acute in the counterclockwise sense with respect to the optical axis. So clockwise is we have to be very careful when we define it so we don't get any mirror effects. So hope that the cameras that we're using here do not make any mirrors, but counterclockwise is basically like this, okay? If in this direction you get an acute angle, then the angle is positive. If you have to go all the way around to get your angle, or another way to put it is if you can make it acute by going clockwise, then you call the angle negative. Okay, so this set of conventions is self-contained and consistent. To add to the confusion, certain optical textbooks, they use the opposite sign of conventions. This is also possible, by the way. The set of conventions I use here is consistent with the Hecht textbook and the majority of textbooks. There's a minority of textbooks that use the exact opposite conventions, but we will not deal with those. Okay, using this set of conventions, we can define the power of an optical system based on whether rays that propagate outwards. So by outwards, I mean a ray bundle that expands, whether a spherical surface, causes the expansion to become slower or faster. If the surface causes the expansion to become slower, as in the top diagram over here, then the surface is said to have positive power. If the surface causes the expansion to become faster, that is, it takes the expanding bundle and spreads it further outwards, then the surface is said to have negative power. Okay. So now let me proceed to define a specific optical system, and then we'll see more examples of this thing happening. So the system I would like to consider is a lens, and this is actually the first example of a lens that we'll see in the class. And I will take a very special case of a lens that we refer to as thin. First of all, what is a lens? A lens is simply a piece of glass that has been shaped to have spherical surfaces on one or both sides. Typically both, but we'll see examples of lenses that are actually flat on one surface and curved on the other surface. So when do we call the lens thin? Well, we call it thin. Consider an expanding spherical wave that propagates through the lens, and consider the maximum angle that can be subtended through the lens. In other words, angles larger than this one would actually miss the lens. So therefore, this alpha maximum is the sort of the biggest angle that we have to worry about. Well, what does the paraxial approximation say? It says that this angle has to be relatively small. So assuming that this is true, then the lens also has a thickness. So this thickness I denoted as T in this diagram over here. So provided this thickness, if we do a little bit of analysis here, we can calculate this thickness relative to the radius of curvature of the sphere and the angle phi that is defined as shown from the center of the sphere relative to the edge of the ray that subtends the maximum angle alpha maximum, okay? So we can see the definition phi for this angle and the radius r. So if given this angle of arrival is alpha maximum, if it is true that the angle phi is also very small, then we can consider the lens to be thin. So we can basically pretend that the space between these 2 points of the lens, the space between the entrance to the optical axis and the exit of the optical axis through the lens, we can neglect the space. This is what the thin lens approximation says. And that's very convenient because we can now analyze the lens. As you can see, if I neglect this space, then the ray elevation before and after the lens remains the same. And also can neglect refraction that might happen within the lens. So basically I have the system where the ray arrives, then is bent and in one step and then propagates outwards at a different angle. So in order to analyze the system now, what I will do is I will break it into 2 components. One of them is the curved surface on the left-hand side, and the second is the curved surface on the right-hand side. Okay. And now for each one of those, I can define an angle on the right and an angle on the left, as I have done in the simple case of the refractive surface. Now, each one of those is a simple refractive surface interface that we know how to deal with from the previous lecture. And I can write equations. Remember the equation for the refraction from the spherical surface. I will write it here on my pad, just to remember. So that it goes like this. Hopefully someone will notice and they will project it. So n to the right, alpha to the right, x to the right, equals, can anybody see? Okay, we're having technical difficulties here. Ah, there we go.
Can you lower the piece of paper? Yeah.
Yeah. So this equals 1, 0, 1. This is easy. And then we have to apply our mnemonic. Minus n to the right, minus n to the left, over the radius of curvature, times the same property for the left. N left, alpha left, x left. Okay. So now what we have to do is we have to apply this rule successively for the 2 interfaces. So here's the equation that we get for the second interface. So in this case, n to the right is 1, because to the right of this interface, I have air. And n to the left is n, because to the left of this interface, I have glass. Okay. Now what I will do is I will apply the same rule, but I will now apply it on the first interface. And if I do it on the first interface, I get this equation. Now notice that in the numerator of the element in the first row, second column, the quantities are reversed because now n to the right is the index of refraction of glass, whereas n to the left is the index of refraction in air, that is 1. So therefore I get this matrix. Now what I can do, I can cascade the two matrices because I can substitute the vector n alpha 1 x1 that is on the top equation, I can substitute it from the second equation. And if I do that, of course, I will get a cascade of the two matrices. And notice that in the cascade, it is very important to remember that in the cascade, the matrix of the last element to the right appears left. And that is very important to remember and not confuse because, as you know, matrix multiplication is not commutative. If you mess up the order of these matrices, you will get the wrong result. So you have to remember that you start from the right, that is, you start from the end of the optical system where the rays depart, and you start cascading the matrices going backwards towards the beginning of the optical system. So this is what I've done here. I've put a matrix corresponding to the second interface. This matrix appears first, and the matrix corresponding to the first interface appears second. And then I cascade them, I do the matrix multiplication, which is a relatively straightforward task to do, and I get the last equation that appears on the slide. Okay. Now let's go ahead and interpret this equation. It looks very nice, but let's see what it really means. Also, before I move on, let me notice one more thing. Notice that in the vectors of the ray angles and the ray elevations, the index of refraction has disappeared. It has not really disappeared, it is simply because the angles alpha right and alpha left are in air, and therefore the index of refraction is 1. That's why there's no index of refraction in that location. Okay. Let's look at this equation again. The top quantity that appears relatively complicated, it has a name, it is called 1 over the focal length. Now, you might wonder, why did I call this the focal length? I will justify that in a second. But if you believe me that the focal length follows from this equation, then this equation is known as the Lensmaker's equation. And it is very useful because it gives you the focal length of the thin lens as a function of the three quantities that define the thin lens: the radii of curvature to the left and to the right, and the index of refraction of the lens. And what I want to emphasize again is that this equation is valid if the lens is surrounded by air. If the lens is surrounded by another material, for example water or oil or something with index of refraction different than 1, then this equation does not hold anymore. And as a bonus, in the next homework, which has already been posted, you will actually derive the corrected equation if the lens is immersed in a material that is different than air. But for now, this equation is correct because we put our lens in air, so therefore everything is fine, and this is the Lensmaker formula. So now let me justify that this quantity that appeared over there and has units 1 over distance, y1 over distance, because this quantity has 1 over the radius of curvature in the denominator, so therefore it is 1 over distance. So let me justify why this quantity is actually the focal length of the lens. So to do that, let me consider a ray that is arriving from infinity horizontally at an elevation x1 with respect to the optical axis. So this ray, I can ray trace through the system. Basically, to ray trace through the system means I have to propagate this ray by a distance z, and then I have to find out what is the ray angle alpha 2 with respect to the optical axis and the ray elevation x2 also with respect to the optical axis as function of this propagation distance z. So now you can see why it was convenient to define the matrix for propagation through free space, because now in order to figure out where this ray lands what is its elevation and propagation angle, all I have to do is cascade the matrix that describes the lens with a matrix that describes propagation through free space. And we've seen this matrix of propagation through free space. It is simply 1, 0 in the first row, and then the distance and 1 in the second row. And it's actually, if you look back at your equation, it is distance divided by the index of refraction. But again, because we're propagating in air here, the index of refraction is 1. So we don't have to worry about this at the moment. And because the free space is following the lens, the matrix corresponding to free space will actually appear first, before the matrix corresponding to the lens. So this is the cascade written correctly here, and we can solve this, and we can find that it is given by this equation over here. So what we observe now is that if we set the propagation distance to, first of all, I did this in the general case, so as the array entrance angle, I left a general symbol alpha 1, but I said already that the array is arriving horizontal, that means alpha 1 equals 0. So therefore, the elevation of the array with respect to the optical axis is given by this equation. It is simply x2 equals x1 1 minus z over f. Okay? And we can see very easily over here that if z equals f, then x2 will equal to 0. So this means that if I let the ray propagate by a quantity equal to this magical amount that appeared in the lens maker's formula, then the ray will hit the axis. So the ray will land on the optical axis. And moreover, we can very easily verify that this happens independently of x1, because as you can see, x1 is outside the parentheses here. If I set this quantity to equal 0, then independent of what x1 was, we will actually get all of the rays to go through the same point of the optical axis. So this is a sense of focus. You can see that the ray bundle that arrived parallel from infinity actually now comes to focus at this location of the optical axis because of these simple equations that we just described. And this property over here justifies the name focal length. It is the length at which the rays come to focus. Okay. The inverse of the focal length, just on its own as a sort of standalone quantity, has a name also. It is called the optical power. And now that's a little bit confusing because in our minds, usually power is measured in watts. Well, this power is not the usual power that we measure as, as energy per time. It is a different power. And for historical reasons, we use the same name in optics, but it is measured in inverse meters. And the inverse meters, they're also known as diopters in optics, and they define the optical power as the inverse of the focal length. So for example, if the focal length is 1 meter, which is a pretty long focal length, you call it 1 diopter. If the focal length is 10 centimeters, it is actually 10 diopters. If it is 1 centimeter, it is 100 diopters, and so on and so forth. Very often, people like myself who are myopic, is anybody in the class audience, is any of you myopic? Anybody use corrective lenses because you have myopia? Okay. Do you know what is the power of your prescription? 0.75. You're pretty lucky. You have very small correction. That's a pretty small correction. Can you say it in your in the microphone?
0.75 in one eye and in the other 1.25.
Okay, 0.25. Is it 0.25 or minus 0.25?
Minus 1.25.
Minus 1.25. Okay. So that is also in diopters. Yep. So it means that the focal length of your lenses is approximately 80 centimeters, right? Yeah. Do you have a... Yeah. Okay. So we will will see later why the correction for myopic people is negative. Mine is also, I'm also myopic, and my correction, actually I have a pretty high correction. Mine are -7 and -5 diopters in my left and right eye respectively. So that means again that the focal length of my glasses is approximately -1/7, which is, I don't know what, 17 centimeters or something like that. Okay. So that is the power. Now, why we use the term optical power? Actually, it is best explained if you look at the final animation on this slide, which is what happens if the ray bundle comes from infinity again, but it is not horizontal, it is coming at an angle alpha 1. So now the angle alpha 1 is not 0 anymore, but I let it be, I let it have a finite non-zero value, and if you do that, then you find relatively easily from the equation over here. Let me write the equation that was we have that x2 equals alpha 1 z plus x1 1 minus z over f. Okay, so if I set z equals f to the above equation, then I get x2 equals alpha 1 times f. This term will disappear, of course. This will go to 0, and z will become f. So get x2 equals alpha 1 times f. So this is the equation for the elevation of the focus for a parallel ray bundle that is arriving non-horizontal from infinity at some angle alpha 1. So you can also write this equation. It is not on the slide. I will just write it on the whiteboard. x2 equals alpha 1 over the power, the optical power of the system. So the power is kind of like a lever. It tells you as you change the angle alpha 1, it tells you how does the elevation of the focus change with respect to the optical axis. So it is basically a gain, if you or a transduction amplification or something like that. It tells you as you change the angle that the rays arrive into the optical system, how does the focus move with respect to the optical axis. Okay. Now, based on these equations that we just described, let's see some different cases of what would happen to the rays. So what I've done here is I put the different types of lenses together with a simple spherical refractor. And the different types of lenses are plano-convex, where you have one convex surface followed by a planar surface, then biconvex, where you have two planar surfaces, then plano-concave and biconcave. So you can see from this that if you have a ray bundle that is arriving horizontal now, horizontal from infinity, you can see that what will happen at the output is actually different depending on the type of refraction that you get in the different surfaces. So I will let you work out, based on the equation, the lens maker's equation, I will let you work out why these cases are all different. But what I would like to do is actually work out the location of the image depending on the different cases, and also see how to ask with respect to the sign convention. So starting, for example, with a biconvex lens, we can see that the biconvex will focus the parallel bundle to the right-hand side of the lens. This is the case that we have implicitly done so far. In my drawing so far, I have assumed that this is the case. However, you can see that if I have a biconcave lens, like the one showed at the bottom of the slide, you can see that each one of the surfaces will actually, each one of these rays will actually expand outwards after it passes through the lens. So in a sense that we described it so far, this lens does not really focus the rays. It creates a divergent ray bundle. You can get a sense of focus if you extend the divergent rays, if you extend them backwards towards the optical axis. If you do that, you will actually see that the rays meet. They do meet, but they meet on the left-hand side of the lens. So now this is an example of focusing that happens not on the right-hand side of the lens, as our equations assumed, but on the left-hand side. And we can now justify this, fact if you actually define Z to be negative and F to be negative. So this is what we call a negative lens, or a lens with negative focal length, or a lens with negative power. And if you do that now, then you will see that the focus will appear on the left-hand side, consistent with our sign conventions, and this is what we call a virtual image, as opposed to the case of the biconvex lens that we call a real image. So this is an example of a sign convection, of the sign conventions, not convections, the sign conventions in action. Are there any questions about this? This is the point where I often get a lot of questions. Let me move on to a different case, and if you think of a question, please interrupt me or say something aloud, pushing your microphone button first. Let me do a slightly different case, which is what happens if you try to, so in the previous example, we saw how a lens can take an object at infinity and focus it to a finite distance equal to the focal length. What I will do now is I will argue that the positive lens actually can take a point object located at one focal distance to the left and image it at infinity. Now, why is that true? I will do this in a second. But you can very easily justify it to yourselves if you simply reverse the orientation of the rays in the previous case. What we did before is we had the ray bundle that was starting from, we had the ray bundle that was starting from infinity and the lens was focusing it. We can very easily reverse the orientation of the rays, and if we do that, then we can see that if I have a point source over here, it will actually get imaged at infinity. Now, of course, according to my sign conventions, this is not the proper way to write it. We have to make sure that the light propagates from left to right. So therefore, the correct to write it is not what is showing over here, simply by convention, not because this is physically wrong, but it does not obey the convention, so we never actually draw something like this. What we draw is what is shown on the slide, where the rays are propagating from left to right. They have a focus that is a point object on the left-hand side of the lens, and then the lens, of course, will collimate these rays. They will convert them from a divergent spherical wave to a parallel plane wave, and therefore will image at infinity. The same thing can be said about a negative lens, except in this case, the ray bundle arriving at the lens has to be convergent and has to come to a focus on the right-hand side of the lens. So therefore, in the same way that this type of lens formed the virtual image in the previous case, in this case we talk about a virtual object for this type of lens. Okay, so let me now try to put this all together so it can make some sort of sense. Again, recall the first sign convention, which is that the light propagates from left to right. If it propagates from the left to right, it means that the object should be to the left of anything that is of interest, and the image should be to the right of anything that is of interest in the optical system. So that is why, if an object is to the left of the optical element, as it is in this case, then we say that the distance from the object to the element is positive. If, on the other hand, an object happens to be on the right of an optical element, as it happens in this case with a negative lens, then we say that the object is virtual and the image from the object to the element is negative, okay? Because it has to be on the right-hand side, whereas in the proper case, it had to be on the left. That's why we put a negative sign. Now, similar things can be said about an image, except now the image is properly positioned on the right-hand side of the optical element. So if it is really on the right-hand side, as it happens with a positive biconvex lens, then the image from the lens, then the distance from the lens to the image will be referred to as positive. Whereas on the other hand, if it happens to be on the left, as it is for the case of the negative lens, then this image will be referred to as negative. This image will be referred to as virtual, and the distance will be referred to as negative. Finally, and I will conclude with this, and I will let Pepe do his demo, is how this applies to off-axis objects. So remember, we derived this equation, x2 equals alpha 1 times f, for an object that is at infinity. Now, for a positive lens, because the focal length is positive, if the angle alpha 1 is also positive as shown here, it means that x2 must also be positive. And this is indeed what we can verify. If we apply Snell's law repeatedly for each one of these rays, we will see that indeed this is the case. On the other hand, if I use a negative lens, where the quantity f, the focal distance, is negative, okay, but the angle of arrival is still positive, then I will get x2 is negative. That is, x2 will also appear below the optical axis, okay? So this virtual image not only appears on the left of the negative lens, but it is also below the optical axis, okay? Now, what about an off-axis image at infinity? I will skip this derivation. It is very similar to the derivation that we did before for the case of an object at infinity. Basically, what I've done here is I have reversed it. I have used an object at a distance f to the left of the lens. I have cascaded the propagation matrix for this free space propagation to the propagation matrix corresponding to the lens, and I have proceeded to solve. If I do this, I will let you do it at home and then come back tomorrow if something is unclear about this. But what I've done is I have solved it, and I find an equation that looks like this. I find that the angle of propagation of the ray bundle to the right-hand side of the lens actually equals minus the elevation of the object divided by the focal length. Or another way to write this equation is alpha 2 equals minus x1 times the power of the optical element, according to the definition of power that I remind you, by definition, equals 1 over the focal length. Okay, so there's a minus sign now, which means that if we apply this equation to our positive lens, the ray bundle that will emerge from the lens will actually now propagate downwards, okay? Because in this case, x1 is positive and the focal length is positive, alpha 2 has to be negative. And negative alpha 2 means that the ray bundle has to propagate downwards, okay? If I do the same exercise for the negative lens, then we can see again very easily that because now because x1, if I pick it to be positive, f is negative, and I have a spare negative sign from the equation, then I can see that the propagation angle, alpha 2, will be positive. That is, the image at infinity will be on the positive side, above the optical axis. Okay? I hope the positive and negative signs are not confusing. Let me restate. When I learned optics, I found this to be also horribly confusing. So I realize and I sympathize how that at the beginning this can be a little bit confusing. I've done my best here to present them better than the professor who taught them to me saw them. And so I hope, because I sort of used my own confusion as a guide, I hope that I managed to make it a little bit clearer for you if it is the first time you see it. But of course, it will become even more clearer as you practice, okay? So the homeworks and the examples that we'll see later, they will make it progressively clearer. For now, what I want you to do between now and tomorrow's lecture is to go back and make sure that these pictures that I've drawn, that they make sense with Snell's law. In other words, what you do is you go to the spherical surface, you imagine a normal to the surface at each point, you apply Snell's law, and you convince yourselves that the rays bend the correct way, and this is consistent with the way the images form, okay? And then you apply all the matrices, all the equations, and so on and so forth. I brought my promise, and I did not leave Pepe with his 5 minutes, but that's because it took us 5 minutes to fix the display or whatever was happening at the beginning. So hopefully you guys can stay for a little bit longer so we can do the demo. Is that okay?
Sure. I'll try to do it. We'll try to do it fast.
Also, and look at the...
So now if we can switch to the cameras, please.
Excuse me.
Okay, so there you go. Okay, so we tried to set up these webcams because last time it was a bit hard to see the demo. So so this demo has actually 2 parts, but today we're just going to show one part, namely the refraction, and we're going to basically witness how Fermat's principle that we've been learning in the past couple of classes, the Snell's law, applies in these systems like lenses or prisms that we've been learning so far. So before actually changing the exposure, let me just show the setup. So we are going to be focusing on this half of the setup. So hopefully you can see it fine here. Let me just move this window. So to avoid any problems about chromatic dispersion or wavelength dependence behavior, we're using a laser, a green laser. So this component here is the laser. Then this is a new component that we're going to call, it's called the spatial filter. These, for now, it has a very interesting properties that we'll learn in the second half of the course when we learn about Fourier optics. For this first part, just think about this produces a very nice point source object. So therefore, after this lens, there's going to be a spherical wave emanating, propagating. So what we want to do after that is to convert that spherical wave into a plane wave, right? So this is what this lens here is doing, and that's what we call collimation. So after this lens, as you can see, well, you'll see it in a second. Okay, so now I reduce the exposure of the camera and I can see the rays. Now I see parallel rays. Hopefully you can see them clearly. Could you zoom in a little bit? Okay, and we have basically parallel rays coming out of the collimated lens. So now this brings another interesting problem. As you can see, our eyes, and we'll see in next lecture, how they are really robust to focusing in different conditions, to change illumination, and more particularly, they are adapted to high contrast in light, like very high intensity in the light and low intensity. Your eyes can see it fine. Whereas this camera, we just needed to change the exposure so you could be able to see that. So this is a problem of dynamic range that occurs in optical systems. So all right, let's look at the first component. It's this lens here. I'm going to put cylindrical lens. It's a plano curved lens here that it's cylindrical. Basically, it means that the surface only depends on the x coordinate. So we'll put it here, and we're going to witness.
If I may interject here, Pepe, if I may interject something?
Sure.
The equations that we derived, strictly speaking, are for cylindrical lenses, right? Because we only use x in our equations.
Yeah.
If you have x and y, then you get a proper spherical lens. So strictly speaking, this is what the equations.
Exactly.
Okay.
So now you can see now the ray tracing, but now done optically. You can see how the rays start focusing into this point here. Well, in this case now, since this is a cylindrical lens, we see that it's a line, and I can put this card here, and we see that we actually form a line instead of a point. All other nice things to see about this lens is that so far we've been ignoring reflections that occur with this lens, but let me just show you some of the reflections in this cardboard here. So we'll see in the second part of the course that these reflections that occur in transitioning from the air and glass interface and back again, so in these interfaces, are very sensitive to the angle of incidence and to the refractive indices of both the lens and the surrounding media. So in this case, you can see that quite a lot of power, so this is the incidence wave, and you can see quite a lot of power is actually going to this side because this lens might not be AR coated or coated with an anti-reflection coating as a better lens would be. So now let's witness Snell's law with this prism here. So you see the little rays here that are going straight. So now I introduce this prism shown here. It looks very dark, but believe me, there's a prism here. And then as soon as I started putting it into the system, you see how the light starts bending to one side more. And then you can see how basically the tilted surface is bending the light, and I can just change the angle. And let's now see the other phenomena that we learned in the previous class, which is TIR. So I still rotate this more and make the angle to be larger than the critical angle, and boom, all the light gets TIR'd, and we can actually see now that it's getting to this side, but in this side of the prism, there's a diffuser, and that's why you see the diffuse light here very bright. So I'm going to do it one more time. Without TIR, all the light escapes out straight through. And now I start rotating this more, and then you see TIR here. There any questions? So I also brought a parabolic reflector for you guys, like the people here in MIT, if you guys want to see the reflection, how your face, look at your face with this parabolic reflector. It's actually quite funny to see the virtual and the real images. And in this case, you'll see, and we'll learn it in next class, how the virtual image generated by such a reflector, it's actually not inverted. It's erected, as it's called. So I'll leave it here so you can come after class.